Oh, it's raining. Yeah, it's raining home. So.
Well,
you notice he's the only one wearing short sleeves. That tell you something about
that's just so a lot.
temperature adjustment.
What? What? The best thing I can answer this one. I know I saw you had it yesterday. I was looking for it. First come, first serve. What? Yeah.
No, not excellent. I know, but he should have been here.
Yeah. They would have been a shootout at the OK Corral. Blood on the tracks. Mark thinks an absolutely correct way about diffraction, but it's very, very hard to understand. And the problem is they're correctly understand diffraction, which are very difficult, and then there are shortcuts, which almost always has something a little bit wrong. Sorry. Where are you now? Ah, yeah, Regensburg. That's one of the greatest cities in Germany. So a few cities in downtown was entirely destroyed by bombing.
Every 2 years they find the bomb at about 2 kilometers away from the center.
Yeah.
Just last week they found one. They had like 8,000 people.
Has any of these bombs exploded in the last 20 years?
They could have been on the news or.
So these things are probably largely. I don't know what the time scale is for the breakdown, chemical breakdown of gunpowder. But it must be some time scale because moisture is mixed.
Right.
I don't know, it's gunpowder, it's probably not gunpowder, it's probably.
So maybe I should just.
Yeah, they're doing some very clever things around bacteria, which will eat up plastics.
Oh,
And
yes.
that sounds like a good thing to put in the garbage dump. But if it mutates and starts spreading, you can fry it. You know, there goes all the wiring in my car, right? It's unbelievable this.
You must. They're made of plastic, so they will start eating us.
Well, you can imagine that you can have something which will be processed because it's so many organic.
It was for those
Deep into the discussion.
I mean,
They're working so hard.
So hard.
Well, either live longer or shorter, one of the two.
In the data, it's faster.
Yeah, you say.
So if we are made of plastic, we should last longer.
Pretty soon they'll discover that a signature for advanced civilizations are plastic bags floating around in space.
So. No. Sorry. Mr. Chairman. Okay, so moving to diffractive scattering as well. Okay, we already discussed also this from a slightly different point of view. But now let's talk about this from the small x physics point of view, and I guess we don't need here very much motivation. But so anyway, I'm gonna consider mostly exclusive vector meson production. I mentioned maybe dijet production at my last slide, if I'm not too much over time. But I mean, the easy motivation why exclusive scattering or diffractive scattering is interesting is that first of all, if you just take like all the Ruskin formula, you see that it goes like 1 squared. So in some sense, this is very powerful probe of the small x structure of the target proton or nucleus. And compared to other processes in exclusive scattering, because you measure everything at the final state, you know exactly what was the momentum transfer here, and momentum transfer is fully conjugate to impact parameter. So this also gives us access to the proton and nuclear geometry.
Since I am. So you have in brackets here 2 gluon exchange. What if I go to higher states? Does the quadratic dependence change in any way, or does it become even more extreme?
I mean, how basically, if you think like you have a small x and you have multiple scatterings, so basically you have, in some sense, you should go to infinite orders, then you also pick up powers of g. I mean, basically we read some. I mean, if you say that gluon densities are like 1 over g, and then you read some powers of g times 1 over g. Well, all over. So in some sense, you have then like, I mean, multiple scatterings, so you have up to infinity.
But then what is G?
But if I'm going,
Then you lose.
one more gluon, you're going up factorization. One other operator.
So then, yeah.
I rest on.
But if you're going, are we talking about exciting a delta or a resonance in the final state, or pure? I mean, at low x, presumably the gluons are universal. So it would be the same. But this is presumably the formula t equals 0.
Yes.
Because there's no t dependence on the right hand side.
Yeah. Then you should plug in some form factor. But this is just, I mean, I'm not gonna use this in this talk or anything, but it's possible. I forgot the reference, but this is from the Ruskin paper from some decades ago. Okay, so as I said, my motivation is to study QCD matter in the upper left corner, where physics becomes nonlinear, but still perturbative, because we generate a scale when nonlinear effects become important, saturation scale QS, and if that scale is perturbative, we hope that we can do perturbation theory in this dense corner of the called QCD phase space. And then when we move to lower x, we have perturbative evolution equations like decay or Zimwalk that tell us how this transition happens. Similarly, as we have D-club that tells us what happens when we move horizontally in this cartoon. Okay, so the two processes that I consider in this talk to access proton and nuclear geometry or structure are DIS and then exclusive vector meson production that look very similar in dipole picture, which is convenient way to study these processes at high energy limit, where this QQ bar flux, the photon fluctuates with QQ bar dipole long before the interaction happens, and then the dipole proton or dipole nucleus scattering, which is what we call dipole amplitude denoted by ENT, then describes how this QQ bar dipole interacts with the target, and this is something that encodes basically all the QCD, interesting QCD dynamics in the scattering process, and it appears in calculations of many different observables. Because then we could have like waterfalls and so on, depending what you are looking for. But in many cases, this dipole target scattering amplitude is basically the only ingredient you need. You need to calculate these cross sections. So if we consider F2s or total cross sections, we can use optical theorem and take just the forward elastic scattering amplitude, an imaginary part of it. Or if we do shape side production or vector meson production, then this is a scattering amplitude that you have to then square. So if you calculate vector meson production, you basically get dipole squared, which is related to the gluon squared I had on the previous slide, like roughly speaking. And I already mentioned that we have these evolution equations that tell us like how, say, BK or Timwalt, that tell us how dipole amplitude evolves when we go to smaller x. So if we have evolution equations, we need some initial conditions for those, and that is considered to be non-perturbative input for these calculations that you obtain basically feeding HERA F2 data or maybe it's a bit some other HERA data sets. So I will mention.
So this is for the forward limit, right? This is an R, not an ER. So you're fitting diffractive F2 from exclusive?
So I will get back to it soon, but basically what you fit is inclusive F2, and maybe it's ARM F2, and then depending on your details of your model, especially if you want to do diffraction, you need some other input like the size of the proton, or that then you have to take from shape side production. You could also study diffractive, like inclusive diffraction, and try to fit that. That hasn't been studied that thoroughly. But I mean, there are works there where you can also compute diffractive PDFs and so that you can describe then the HERA measurements. Yeah, I'm not considering inclusive diffraction in this talk, but that's actually not something that is also probably very useful observable in the EIC era. So this is the same diagram I had previously, but just to show you how technically how the geometry dependence comes in and how this factorizes nicely in the high energy limit. So you have, as I said, the virtual photon splitting to a dipole. This is something you compute on QED. Then this dipole scattering, as I said, this encodes all the multiple scatterings of the part with the target color field. And then if I do shape side production, I have to form a shape side from the dipole. And this is actually something we don't really know how this happens, and this gives us some model uncertainty in this picture, but also something that we should really improve our understanding of the vector meson part here. So then you're gonna calculate the cross section. You have to basically the virtual photon wave function.
I don't understand that. That's why.
Textbooks have been telling us that it works perfectly for decades.
What?
The J-psi wave function.
Well,
QC perturbative.
Yeah, but for example, when you consider J-psi wave functions, that most constraints you have, they come from the leptonic PK, and that draws the wave function at origin at r equals 0. But then when you calculate like formation of a shape side from a dipole with some size, then how we usually constrain our parameterization for shape side wave function, our input is just the decay, which is value at r equals 0, and then we say that okay, it needs to be normalized, and then maybe you can use like the mass. Yeah, and it's like okay. I guess these two.
So
You assume it looks kind of a virtual photon. It has a similar spin structure and so on. It must be normalized, and it has to be the correct value at the origin. But this gives you quite some freedom actually.
And the lattice doesn't improve.
My understanding is that I mean I haven't heard much from lattice point of view. Non-relativistic UCD studies are, I think, an interesting way here. Of course, the question is if you can do an RQCD with charm, maybe it works better for upsilons.
So if you were not using an RQC, you would just plug in some kind of boosted Gaussian and then just have one parameter which is the function of the equation.
Yeah, I mean, that's what constrains it from the.
But so yeah, if you were using an RQCD in that case, since it's exclusive, you only have to fit the singlet, which is always the wave function at the origin or derivatives of the function. But this is all physical, so contrary to the inclusive cases in which you would have octet, which is not physical. So maybe an RQC would be at least a good idea to try.
Yes, but yeah. So at this point, these NRQCD studies have not really been applied in this framework, but this is something we have been somehow slowly planning to get into at some point. Okay, let's keep. Okay, then I want to say that okay, when you calculate this as function of momentum transfer delta, then you end up fully transforming this from the coordinate space where B is the impact parameter to the transverse momentum space, and this gives you the access to the impact parameter dependence of the dipole scattering amplitude here. R is the size of the dipole, and X is basically X pomeron. Roughly speaking, the Birkenhead of the diffraction. Okay, so I'm gonna talk about two different classes of diffractive events. So we can either have a process in which target proton or nucleus remains in the same quantum state that we call coherent diffraction, and then it turns out that the cross section is average over the scattering amplitude that I had on the previous slide, average over the different target configurations. So basically, for each target configuration, I have different dipole amplitudes that depend somehow on the impact parameter or density profile of my target. And then, so I average this, which means that this is sensitive to the average density profile, and then I take the square. You see here, if I take the average over different configurations, I just get the average dipole, which is sensitive to the average density profile. Okay. On the other hand, if I take the total diffractive cross section and subtract this contribution, I'm left with events where I require a target to break, or dissociative processes I think that that's the term used in many HERA papers, proton dissociation, or I usually talk about incoherent diffraction here. And this is a variance. And if you see a variance, you are measuring some kinds of fluctuations in the dipole scattering amplitude. So it measures how the lumpiness of, or how much different, how different the dipole amplitudes are between different configurations of your dark target. A different length scale. Then the length scale is set by momentum transfer because it's a Fourier transform. So if you have large momentum transfer, you are talking about short distance scales and vice versa. Okay.
This was for small momentum transfer.
Okay, so then we hope that we can push the validity of the framework to the t values that basically are covered by HERA measurements. We don't go up to very high t, but then this is like how.
But I mean, this one here is only valid if t equals 0. Otherwise, you would have non-diagonal contributions.
Yeah. So this is I mean, at very high t, this breaks up. Then the question is like, up to how large t you safely.
So this is very interesting then. So this means that at small t here, you would be probing the, let's say, mean field approximation, and then doing the same for large t would probably non-diagonal terms. That's interesting.
That's actually, okay, this is different way of seeing that. Okay, so let's look at the HERA data. So in various dipole model calculations, so we have been very successful to describe this large amount of precise data we have from HERA. So in this talk, I'm going to usually refer to two different ways to obtain the dipole amplitude n. I don't go into details how they look like, so I mean you either know them or just I can give you roughly speaking what they are. So IPSAT is something where we have some parameterization for the European X dependence of the dipole and for the impact parameter dependence of the dipole. And it's nice because then in the dilute limited there is a smooth matching to debug and somehow polynomial factorized result. Dating back to like Kowalski papers, and then initial condition for that is obtained again by feeding HERA structure function data. Or the other approach is to use some dipole, obtain dipole that satisfies the vector evolution equations like PK or symbol, and then feeding the initial condition for those. In most of the works in the literature, you don't usually consider impact parameter dependence here, but then if you don't know the impact parameter dependence, you cannot do diffraction. But there are also some works by Anna and also we did Björn Schenke some time ago where you also try to include impact parameter dependence in this work. So I mean this is just some Q-squared pins of reduced cross section, which is roughly F2 from HERA, and the uncertainties are tiny, and no matter what dipole model fit you take, you basically have a perfect description here. And then, if you have also some description of the geometry and take the IPZ parameterization, that's basically perfect with reduced cross-section data, and then you can look at shape side production, row production, DBCS over somewhat wide range of kinematics, and the descriptions are basically perfect. So far so good. Okay. So now I was talking about the fluctuations, or now different variances of the diffractive scattering amplitude. And in order to get that, we of course must have some event by event fluctuations for the dipole amplitude. Now, our approach here is to think that these fluctuations are fluctuations in the transverse coordinate space density distribution. And we take with Björn Schenke, we took a very simple constituent part picture, kind of inspired picture that says that okay, small x gluons are located around 3 hotspots. It's not really necessary in this context that there are actually 3 hotspots. Then you can play the game and also work with different kinds of geometries. But anyway, you must have something that fluctuates from event by event to obtain non-zero incoherent cross section in this picture. So we say that okay, our proton density profile is sum of 3 Gaussians, so it looks something like that. And then we can use constraints from coherent diffraction, which probes average density, and incoherent diffraction, which probes the amount of fluctuations to constrain the parameters that describe how much this proton fluctuates. So basically, you can parameterize, say, the width of each of these blobs, and then you can parameterize from how far from each other they are usually sampled. And this is one of the examples that we get. So we take the simple IPZ parameterization, and so we can play the game where I can take very smooth protons that fluctuate very little, something like that, like this here, or I can take protons proton that fluctuates quite a lot, so taking small blobs that are sampled relatively far away from each other, they claim that the average shape is always roughly the same. So the solid symbols here are H1 data for coherent shape type reduction, and open symbols are H1 data for incoherent shape type reduction as a function of T. Now in both cases, so red lines are with these lumpy configurations and blue lines with smooth configurations. Coherent cross-section is basically the same. Incoherent cross-section, which measures the lumpiness, the amount of fluctuation, is very different. So in this case, the parameters are tuned to get this data to work quite well, and in this case, that's just some random parameterization, which is quite smooth. You see that the incoherent cross-section is way like orders of magnitude below the data. So this already suggests that we need large event-by-event fluctuations to describe the HERA measurements of incoherent diffraction.
Question. In the lumpy pictures, in addition to the parameter for the Gaussian width of the lump, do you have some description of the randomness of where the three lumps are in the?
Well, I mean, yes. I mean, basically, we have two parameters. One is the size of the blob, and the other one is how far they are sampled. So that basically.
Is that a Gaussian for the also?
Yeah, that's all.
Separations?
We also take that to be Gaussian. Then this actually by construction gives basically the same Gaussian that you, if you just take, I mean this must give some, I mean this is the Fourier transform of the average profile. So it's Gaussian. So I mean with this if you take the average, this also sums up to a Gaussian. And basically we do it by something from Gaussian distribution positions for the Gaussian plots.
There is a little bit of tension at very low T.
Yes.
Which would imply large B, which would imply that there are more tails than you.
Okay, so in this plot still I only have geometric fluctuations. On top of that, if we add fluctuations of the overall density, these fluctuations take place at larger distance scales, so they manifest themselves at small t. And also, for example, in this plot, it starts to work better. This is also a different, so this is also going to a more prettier pictures. So I changed from IPSAT parameterization to actually MP model, where we sample color chart fluctuations. Sorry, we sample individual color charges, so the Young-Mills equations to get the Wilson line. This is if you know the IP plasma framework for heavy ion collisions, this is very similar to what they do there for the initial condition. So then this is basically a plot of, let's say, the color charge density. And now, if we have a round proton with only color charge fluctuations, the incoherent cross-section is here, which is very small. Now I tune the parameters to get, again, large geometry fluctuations. And on top of that, we also have to add some fluctuations of the overall density to get really the smallest t part also. So actually the overall density fluctuations only affect the incoherent cross-section in this region, and then if you go to higher t, you are more sensitive to the geometry fluctuation. And then actually one nice work we did with Björn Senke and other BNL guys was to take these protons and then do hydro simulations of PA collisions. And then in this paper you see that we get actually very nice description of, say, flow harmonics and some other LHC measurements of PA collisions where you see interesting collective effects. But then when we have these nice protons, or in this case I can just consider also without the hotspot substructure for simplicity, so I have just round protons with some color charge fluctuations, and then I can take a Jim-Walk evolution. I fix my alpha S or lambda QCD if I do running coupling by requiring that I describe the charm F2 data from HERA, and then I run Jim-Walk. Then I also need to need to constrain somehow I have some Coulomb tails that I have to regulate. Without going to these details that you find from the paper, I can calculate, say, how fast my proton grows. Starting from x to -2, going to some smaller x. And what we get are shown here. So this is the slope of the coherent shape size vector, which measures the size of the proton. Like I saw here, as a function of energy, there is some metadata. And in two of our calculations with Dixon running coupling, we quite nicely described this. So this is not a fit to this data, but because the evolution speed is constrained by charm F2, which is not sensitive to geometry that much. Okay, then I can also study how the substructure evolves as a function of energy. I take this kind of a fluctuating hotspot tree-blob structure, and each of these configurations I evolve separately to small x, and then I can calculate diffractive cross-section at small x. So at this energy, this parameterization is fixed to this Hera data here. To basically, it fits incoherent and coherent cross-section perfectly. So if I calculate the cross-section ratio, I'm basically on top of the Hera data by construction. But then I can predict the evolution. Of course, there is not much data at larger energies, but at least we kind of describe the trend here. For comparison, there is an IP-SAT result where I again use some parameterization to be in rough agreement with the Hera data at this energy. But in the IP-SAT, when you go to small x, you basically just scale your QS. So the density grows up, but there is no geometry evolution, so this is roughly flat. But then from Simultaneous evolutions, we also describe this evolution quite nicely. And this is actually also.
I have a question.
Yeah.
So if you do Simultaneous evolution, your proton is going to get very big. But it's not just Simultaneous evolution that you do. Why the overall size? It seems that it doesn't increase a lot.
Well, I mean, this is how much it increases. I mean, of course, there is
a lot.
I mean,
because it's supposed to diffuse in the large peak, right?
So we regulate the Coulomb tails.
So there is okay.
So that gives me one additional parameter that.
So now, how crucial is this parameter? How crucial is this regulation to get the data?
Well, I have some constraints that I also need to be compatible with F2 charm data. But I mean, of course, there is some room to play. So I could make this to grow somewhat faster or slower, and still
you can play with this regulation.
Yeah, so it's no.
But also if it grows faster than F2 charm, for example, grows also faster. So I have some constraints. So some of the idea that the game I'm trying to play is that I want to simultaneously describe like inclusive data sets and exclusive data. But you are right. That there is some
The question is how is sensitive to the non-perturbative tail and the way you cut it off, or are we really sensitive to perturbative G1?
Yeah. So I think we did some. I think we have some thoughts about the cutoff or damping factor dependent in the paper. So yes. So there is some freedom there. Yeah. I'm quite slow here today. So this is actually, so what we saw here is that this cross-section ratio goes down towards large energies, and this is compatible with what we actually see in some ultra-peripheral Alice data. So they do ultra-peripheral PA collisions, which are basically photon-proton scattering, and this data is still only in this kind of raw form, but this is the shape-side DT spectra, and this is at low energy for photon-proton system. This is high energy for photon-proton system. At low energy, you have the coherent peak here, and then towards high momentum, you have the incoherent background. background, let's say incoherent contribution. And when you go to high energies, you still see the coherent peak, but no incoherent contribution here. So this kind of, I would say that it gets, in this picture, smoother, at least on longer distance scales when you go to high energies. And then if you look at more recent ALICE data, you see clear transition. They have also intermediate energies between these two ranges, where this incoherent seems to disappear towards large dipole. Okay, so far so good. We have nice description of large variety of data. But then there are still some quite large theory uncertainties. I have a couple of slides about the large dipole contribution. That's a bit annoying. I mentioned about vector meson wave function that we don't know quite well. If you play with different parameterizations, you have some like 50% uncertainty in your diffractive cross sections. Then you may have heard about the skewness correction if you have two gluon exchange and the gluons carry different value of longitudinal momentum. This gives you again some correction that you can compute if you think that the computation can be applied in this picture. Then of course NLO, we will probably learn about NLO next week.
Skewness is 50%.
Depends on kinematics, could be up to 100.
Yeah. It's huge.
It's
I
huge.
thought it's much smaller.
No.
Yeah, depends on kinematics a bit.
And you need it to describe the cost of the data.
So one a bit, I mean, this is not really surprising if you have ever thought about this, but if you calculate like F2, you need quite large dipoles, even at high Q squared. So on the left, I saw how large fraction of F2 is recovered if I only integrate up to certain maximum dipole size into IPSAT parameterization. So in IPSAT, if I have a huge dipole, 1 meter dipole, it's scattered with probability 1. So now if I look at the Q squared of 500, even at, and then I go to like up to 1 Fermi, I still have like 10% of the F2 that I don't get. So like at like 10% of the F2 at large Q squared, I get from dipoles that are larger than 1 Fermi, which is maybe a bit annoying. But of course, you can think that okay, this kind of an effective description of large dipoles. It should be maybe some ion target scattering or something that scatters with large probability. On the right, I saw the same similar calculation for exclusive shape size reduction. Here, you need to go up to maybe 0.6 Fermi to recover most of the cross section. And if you look at F2 charm, you only need to go maybe up to 2.3 Fermi. So there's kind of a quite clear ordering of dipole size that contributes to different observables. And this is important because if I now take the MB model that I evolved with SimWalk previously, here the large dipoles behave completely differently. Because in the MB model, if I have large dipole, both quarks miss the target, and the scattering probability goes to 0. And the result of that is that if I now take this MB model, evolve with SimWalk, compute my F2 as a function of x, I am way below the Hera data. And this is not really surprising. So on the right, I saw the dipole amplitude as a function of dipole size. The dotted line is IPSAT. And as I said, it's parameterization that always goes to 1 at large dipoles. And in the MB model, of course, the large dipole behavior is very different. And so it's not very surprising that we underestimate the F2, and we also underestimate the normalization of diffractive cross sections. Well, of course, then one can argue that we have to add some kind of a non-perturbative contribution. So I for one example, I took what Anna did some years ago, and say basically the idea is that okay, dipoles larger than some size which is comparable to the proton size, at roughly scattered with probability 1, and then if I add that, then I can describe the F2 data, but it's a bit, I mean, it's also asked me a couple of extra parameters, so it was surprising that if I add some some contribution with 3 parameters, I can describe the data. Okay, so that was what I have done with Hera data, or me and other people have done. And for the last couple of minutes, let's go to higher densities with nuclear targets, because this is supposed to be EIC. So with Hera, it's not really clear that we see saturation effects or nonlinear effects. So we can obtain exactly the same quality of the data description when if we use linearized models without any nonlinear effects. For example, I can take linearized version of IPsat that I denote by IP-DONSAT, fit the parameters. You don't even see any difference when I calculate structure functions, or if I calculate vector meson production cross section, they are also very similar. So need higher gluon densities than what we have at Hera. And of course, the answer is to go for nuclei, because increasing A is much cheaper than decreasing X. And then at the EIC also, it would be very interesting if we could vary A, so we could probe nicely different saturation scale values. And we already have quite a nice data from the LHC and also from RIC about ultraperipheral collisions. So this is the CMS analysis data for shape side production as a function of rapidity. And if you just take proton, like a shape side production of proton that's measured at Hera, and scale that to nuclei, you get using something like impulse approximation. You would expect the cross section to be in this band, but then you find that the cross section is heavily suppressed with nuclear targets. And this is also visible in this model comparison from one of the earliest Alice papers in this business. So if you just take like a scaled proton PDFs and calculate shape side production using something like Flusking formula, I think you get something which is clearly overshooting the data. And then calculations that use nuclear PDFs or saturation models like IPsat, they are pretty much compatible here. In my case, if I look for the nuclear suppression factor, now you have to be a bit careful with the normalizations and so on. Because in exclusive scattering, scaling factor is not coherent diffraction. In coherent diffraction, the scaling factor is not just trivially like A or A squared, but you can work out the proper normalization factor that gives you unity in case of absence of any nonlinear effects, which is this dotted line here from IP-DONSAT calculation or linearized IPsat. And then I can look for, say, Q-squared dependence of this nuclear suppression factor for different vector mesons at different energies. So, for example, for shape psi, this is the suppression factor at 100 CeV, and then at something like LHDC energy range, we get not that much energy dependent actually here. If you go to lighter mesons, for like rho and phi, you of course expect to see much stronger nonlinear effects.
So, what is the conclusion on your previous slides? So you actually have a saturation effect at the LHC, or
I mean,
this is big.
Yeah, I mean, even from here, if you just naively take, if you naively scale proton result to the nuclear targets, you expect very large cross section compared to what you get from the data. So there is something you can call it shadowing nuclear PDL.
But the orange band is the nuclear PDL for its saturation model.
Well, I think this is actually this leading twist.
The Cousy,
yeah.
Strickland.
Okay. I don't know, Mark is not here. So
I'm just naively asking if this is the smoking gun or it's like.
Well, I mean, you definitely
can describe it with some simple nuclear PDFs regardless.
Yes, I mean nuclear PDFs. My understanding, I don't know exactly how they Adeluni Bertolani calculation with EPS09 works. That goes exactly through the data points. Of course, I don't know if that goes. But so I think they just take basically the Ruskin formula and plug in the EPS09 nuclear PDFs. I might be mistaken, but that's my, should be quite straightforward. But the problem with when you use nuclear PDFs here is it's exclusive process. And nuclear PDFs are by definition inclusive quantities. You measure them in inclusive scattering. So if you try to use nuclear PDFs here, I'm not that convinced that it's really.
So you think what they do is they just take the gluon and they square it.
Yeah.
They use the formula.
Yes.
That doesn't really make sense. This formula, first of all, it's a leading order.
Yeah.
They're using NLO PDFs.
Well, for EPS, I mean, I think there is leading order also.
Why PDFs are not GPD? This is exactly where you should look your GPDs.
Yeah, it would be much better to use GPDs.
Why don't they use?
Because most people are prejudiced against finite T. It took a decade for Anatoly to ever write anything about T dependence, even though he was writing papers about GPDs the whole time. And similarly for Mark, I always wanted to be at T equals 0 because it's a simpler.
Yeah, with nuclear target, with heavy nuclei, you are very small T thanks to the nuclear form factor. So I think this kind of helps it to be a bit more rigorous, I think. Okay. So we can also calculate the kind of suppression factors. I don't have data comparisons here at this point, but at some point we probably have some. I mean, of course, the UPC data is only photo production, but still we should look at. I guess in this picture we get a bit too less suppression as we already discussed like yesterday.
So the blue curves are the W equals 1,000.
Yeah. LHEC. But then, okay, I kind of running out of time, I guess. But then you can also try, if you have large enough Q-squared lever arm, you can try to see the transition from dilute to dense region. So you say, okay, when Q-squared is much less than QS squared, you are enhancing your nonlinear effects. And then when you go to high Q-squared compared to QS, then of course you should recover the dilute limit. And so this is one example we did with Ratsu some time ago. So okay, we parameterize that the cross section goes like total cross section goes like Q to some power gamma, extract this gamma as a function of Q squared, and then when you go to the in dilute limit, you get something which is very different than what you get at low Q squared, where you enhance your saturation effects in this picture. And then with high energy machine, high energy IC that can have large Q squared lever arm, you would study something like that.
What's QS squared?
CV squared. This is from the white paper, right? I'm gonna skip this, but this is a simulation that has been done that you can how to extract nuclear transfer geometry from the coherent cross section. Okay, so I actually didn't skip it. One thing we have, you can also do with light nuclei, is that you can ask like how well you actually know, say, deuterium substructure or helium-3 structure. And one motivation we have, so this is in work in progress with Björn Senke, we had when we did this, to do this is that say you have T-cold measurements at the rig, and then you may want to say apply hydropixel. And then the question is like, how are small X gluons distributed? You have like Haugen wave function that tells how far apart like proton and neutron are. But then is there something like in between? And if there is, then it should affect how your density profile, average density profile looks like. So we can calculate, say, the coherent cross section for scattering of neutrons. But okay, then if in this plot I haven't played the game, but I can play the game and say that okay, maybe there is some I don't know, core flux tube in between, then it clearly affects what you see here. I mean, we basically we know from nuclear physics, we know the neutron wave function in terms of the separation between proton and neutron, but do we really know how it looks at very small x? Maybe not. Okay, I have some time left still. So I mentioned this at the beginning that T gives the scale that we look in the coordinate space. So if we have small t, we look at long length scales. If we have nucleus, we see basically fluctuation of the nucleon positions. So we can sample positions for each nucleon from the Booth section, and then this gives some contribution at low t for the incoherent cross section. But if each of these nucleons have a substructure, then when we go to high t, we start to see effect of this substructure. So this is from a work with Björn Senkelvik. We studied two different pictures for the nucleus. In the solid lines, or let's say in the dashed lines, we have no subnucleon structure. So protons and neutrons are just round balls. And this is the coherent spectrum where you see some nice diffractive peaks. And with and without the substructure, of course, the average geometry doesn't change. So these lines are basically on top of each other. But then if I look at the incoherent cross section, and when I go to large enough t, I start to see separation between my nucleus that has nucleon substructure, solid lines, and the nucleus that has no nucleon substructure. But at lower t, the incoherent cross sections are the same, because at lower t, also in the case with substructure, we are basically only see the longer distance scale fluctuations. Okay, how much time I have?
Time for 2 slides more.
1 minute. Okay. Okay, so maybe if you want, we can discuss later on about one of the proposals we had with Thomas Lappi and Ratsu about centrality and diffraction. I want to also mention on my last slide something we have been doing recently. So to go beyond, or go more differential. So consider diffractive dijets in this case, where you actually have not only one momentum, but two. So it gives you more handles of the geometry, or it gives you more detailed growth. So basically you have the vector sum of the dijets and the difference of the dijet momenta that you consider. And it has been argued by Josi and Bowen and collaborators that this is sensitive to the gluon with the Wigner distribution. So both transverse momentum and transverse coordinate dependence of the gluon distribution. And one thing, for example, that we see here in this picture is that there is a dependence on somehow the dipole amplitude depends on the dipole orientation. So if the dipole is oriented parallel to the impact parameter, it prefers to scatter with higher probability than if it's perpendicular to the impact parameter. So it's shown on the right here from, well, it says high peak plasma, but that's basically MB model, that if you calculate dipole amplitude as a function of the angle between the dipole orientation and the impact parameter, it's not actually surprising if you have ever done anything like this kind of calculations. But anyway, we see that the scattering amplitude is higher when the angle is 0 or pi or 2 pi. So when it's parallel, and so there is kind of B2, if from heavy ion physics language, there is a B2 in the dipole amplitude. And now when I calculate diffractive dijet production as a function of angle between the sum of the dijet momenta and the difference of their momenta, we see the same B2 structure here. So, for example, the solid line is the total dijet production cross section as a function of this angle.
Remind me, how do you get RD experimentally?
No, you don't. You integrate over them. But this is what you get experimentally, and you get the same B2 structure here. So if I now take just IPSat, where there is no dependence on the dipole orientation, then the dipole amplitude as a function of angle is just flat. Then it's not shown here, but if I plug in this IPSat here, the cross section is just flat. This is shown also in paper by Amir and Guillaume and others some years ago. So if you have, say, MP model where there is dependence on the angular dependence, there is dependence on the dipole orientation with respect to impact parameter, then this manifests itself also in the physical observable, which is integrated over all lines.
So this is the sigma d what?
This is the cross section as a function of angle between the dijet, total dijet momenta, total moment.
QT and PT.
Yes, it's based almost the same definition as in your paper. So.
Are there any decay channels of the J side that would be sensitive to intensive polarization?
But okay, this has nothing to do with J side.
This is dijets.
This is dijet. I go, yeah, so maybe it's clearly said. So, but the last line, I wanted to go beyond one particle production. Actually, polarization study, like polarization, but also in case of J side, that might give us something I'm not really certain.
Should you see this also in UPC dijets?
In diffractive dijets, yes. In inclusive, ask yourself because you you computed that.
Okay. Yeah. Again, this is for small t. Right? Small dipole sum.
This is how is the Yes, this is small t kinematics. If t equals 0, of course, but there, I think t is much less than the 2. Yes. Okay, but this is something we are doing with Björn and Niklas Müller right now. Okay, so my last slide. So complementarity, I didn't really. Okay, I had some UPC result. There is of course much more than I was able to show. So complementarity of the high energy UPC measurements at the NHC with the EIC that has Q squared and A lever arm opens up many possibilities. Just this is just some list that some list in random order of random things that some of those I think I was talking about, but observing saturation effects, resistance studies. Maybe we can understand the vector meson wave function better. Maybe it helps if we have Q squared, clever arm, also QS squared, I guess. Weaker distributions become possible. Maybe with this issue with large dipoles, maybe we can start to understand some of the confinement effects. Inclusive diffraction, I didn't discuss, but this is also very, very interesting process. As we expect, the diffractive cross section is heavily enhanced in nuclei, and then also this question of centrality in EA is quite still an interesting possibility. So interesting fundamental physics and also necessary input to LHC heavy ion studies coming into EIC era. Thank you.
To go back a few slides, about 26, where you're talking about it's here. So, for example, so these hotspots here, you're talking about hotspots in the deuteron and the nucleons. Earlier, it was the hotspots in the proton, which was which was quark or constituent quark, so to speak. But in the initial state, if you have a polarized deuteron, combining different vector intensive polarizations, you can actually compare these states, and so this should greatly enhance
the
asymmetry.
So you say I am prepared to be like if I with respect to beam axis, like
yes, I think you can.
Like yes, so I mean whether the proton and neutron are like aligned along the beam or shadowing each other with Mark or
yes.
Yes. Okay.
since the rich folks now say they can accelerate gluons, doing DA with polarized gluons,
Accelerated, we can.
you can do it in your mind. but the protons, but again, protons, we know that if you have a transversely polarized proton, the up and down quarks separate. Now, I'm not sure in the models whether that persists at low x. Maybe it doesn't so much, but nonetheless, it would seem to be polarized protons on nuclei, transversely polarized protons on nuclei could amplify these effects, and it could be very interesting. I mean, that is technologically possible, right? With existing.
Vicky, when you played with that, at some point, if you go to very low x, you turn black.
Yes. Can you yes?
Then you're incoherent.
Yes.
Have you played with that when that actually becomes?
No, I don't see that happening in our calculation. So there is this. I have I reference this Sepila and Takaki. They have this calculation where when you go to smaller x, you add more of these hotspots, and that way it becomes black much faster. And they actually get something, so they have this like incoherent cross-section function of W, which looks like this. We don't see anything like that, at least in any realistic kinematics that we consider.
I'm just asking, like, for example, if you go to LHC, what
this is, I mean, black is if you are
if you very low x, at some point this thing in A at least must turn black.
But so H is never black. But of course, the H gets smaller compared to the black center. Yeah, but
That completely depends on your profile.
so I
How
mean,
many hotspots you put.
yeah. So I mean, I guess we haven't done evolution, symbolic evolution with nuclei yet. But in that case, we would hope to see something like that happen.
So what kinematic range are these?
So
Double dijets. Yeah, we talked about.
Dijets. So they end up in the EIC, easily in the EIC kinematics. We put the cuts such that they are. I mean, the transverse momentas are of the order of GeV, and then rapidities are such that I don't remember exactly, but they should easily end up in any reasonable EIC.
You had something before you skipped, which sounded interesting. What was that?
So I mean, this is the older paper we did with Ratsu some time ago. So the idea was that if you do incoherent diffraction, in incoherent diffraction of nucleus, so momentum transfer is quite large, so it's localized to small area. Or you can think that you have a diffraction of an individual nucleon that you kick the nucleon, and so it propagates through the nucleus on its way out, and it may kick other nucleons out. And then, if it's more central event, there are more of these ballistic nuclei. Now there is also another source of nucleons, so you may excite the nucleus, and it decays and emit some neutrons and protons. But those have different peak spectrum. So so then, if you look at the kinematics, then these ballistic nucleons, they have PT, which is between, I don't remember exactly, 0.2 to 1 GeV or so. So then we looked at some EIC simulations this is for DBCS, but anyway, this is the acceptance of Roman pots, and there seems to be pretty good acceptance to see Roman this kind of nucleons or protons that have BD of the order of GeV or so.
This could be, why you say protons, could be neutrons.
Yes, but neutrons you cannot separate from. For neutrons you cannot separate this ballistic component and the component that comes when your nucleus decays, because they end up in the CDC.
Mm-hmm.
And then you I don't think you see their PD distribution, for example. So the idea was that if you look at the protons, they end up in Roman pots, and you see the Roman pot if you had a lot of those or just one. And then you could say that the events where you have more stuff going to Roman pot are central. And then we computed, for example, shape psi to rho cross-section ratio in central events compared to the minimum bias. And then, okay, maybe you shouldn't look very low Q squared because this is rho production, but still, if you go to lowest Q squared, you see basically that the light mesons are much more heavily suppressed in the central events that are associated with large number of protons in the Roman pot compared to minimum bias. For neutrons, this doesn't work because you cannot separate the two components.
Well, you can partially separate them because the thermal neutrons have a much narrower angular spread than ballistic neutrons.
Yeah, but then you need a fine granular CDC.
Yes.
Okay,
There are lots of reasons why you need a high quality hadronic coming in the forward direction. And this physics drives the granularity that you want, and light nuclei drives the energy resolution that you want. So.
Exhausted the questions.
For now.
For now. So what was the time?
30.
2:30.
Very good. No change in this. Good.
Shall we thank Heidi?
Yeah.